For centuries, Isaac Newton's law of universal gravitation reigned supreme. It explained why objects fall to the Earth and why planets orbit the Sun. Newton described gravity as a force acting instantly across vast distances. This idea worked well enough to predict the motion of celestial bodies. However, Newton himself admitted that he did not understand the true nature of this force. In 1915, Albert Einstein forever changed our understanding of gravity. He proposed his general theory of relativity. It wasn't just a new theory, it was a radical new way of thinking about the universe. Einstein did away with the concept of gravity as a force. Instead, he described it as the curvature of a four-dimensional fabric called space-time. Imagine a bowling ball placed on a trampoline. The ball creates a dip in the fabric. This is similar to how massive objects like stars and planets warp space-time. Smaller objects like planets or even light itself then follow the curves in this warped space-time. This is what we experience as gravity. Einstein's journey to general relativity was not a walk in the park. It was a long and arduous climb, fraught with challenges and setbacks. It took him nearly a decade of intense thought and rigorous mathematical exploration to fully develop his revolutionary theory. Einstein's first breakthrough came in 1905 with his special theory of relativity. This theory dealt with the relationship between space and time, demonstrating that they were not absolute but intertwined. However, special relativity only worked in the absence of gravity. Einstein was determined to find a more comprehensive theory that could explain gravity within this new framework. The mathematics involved was incredibly complex, even for a genius like Einstein. He had to immerse himself in the world of non-Euclidean geometry and tensor calculus, pushing the boundaries of his own mathematical understanding. There were moments of frustration, periods of self-doubt, and times when the solution seemed hopelessly out of reach. As Einstein grappled with his theory, he wasn't alone in his pursuit. Across Europe, another brilliant mind was working on a similar problem. David Hilbert, a renowned German mathematician, had also become intrigued by the challenge of unifying gravity with Einstein's earlier work. Hilbert and Einstein engaged in a lively exchange of ideas, sharing their progress and challenges through letters and occasional meetings. This intellectual rivalry, while cordial, fueled a race to the finish line. Both men were determined to be the first to crack the code of gravity. The pressure intensified as both men neared the solution. Einstein, presenting his work to the Prussian Academy of Sciences, laid out the framework of general relativity. Meanwhile, Hilbert was independently developing his own set of equations. The race to publish a complete and consistent theory was on. While Einstein and Hilbert raced to complete their theories, the world remained largely oblivious to the scientific revolution brewing. Einstein knew that he needed a way to test his theory to provide concrete evidence that would convince the scientific community. His theory predicted that gravity could bend the path of light. This effect, however, would be very small and difficult to observe under normal circumstances. A total solar eclipse provided the perfect opportunity. During an eclipse, the moon blocks out the sun's light, allowing astronomers to observe stars that appear close to the sun's edge. If Einstein was right, the sun's gravity should slightly shift the apparent positions of these stars. British astronomer Arthur Eddington, a staunch supporter of Einstein's work, organized 2 expeditions to observe the total solar eclipse of May 29, 1919. One team traveled to Sobral, Brazil, and the other to the island of Príncipe off the coast of West Africa. Section 5, Warped Starlight, how Eddington proved Einstein right. The expeditions faced numerous challenges. The weather on Príncipe was particularly worrisome, with heavy rain threatening to obscure the eclipse. But as fate would have it, the clouds parted just in time, allowing Eddington's team to capture photographic plates of the eclipsed sun and the surrounding stars. The analysis of the photographic plates was meticulous and time-consuming. The fate of Einstein's theory hung in the balance. Finally, the results were in. The stars observed near the sun's limb during the eclipse did indeed appear slightly shifted from their normal positions. The amount of deflection matched precisely with Einstein's predictions. The news of Eddington's findings sent shockwaves through the scientific community. Einstein became an overnight celebrity, his name synonymous with genius. general relativity, once a controversial theory, was hailed as a triumph of human intellect. Section 6. A new cosmic framework from black holes to the expanding universe. The confirmation of general relativity wasn't just a victory for Einstein, it ushered in a new era of astrophysics and cosmology. The theory provided a new framework for understanding the universe on the grandest scales. One of the most intriguing predictions of general relativity was the existence of black holes. These are regions of space-time where gravity is so strong that nothing, not even light, can escape. While we couldn't directly observe black holes at the time, their bizarre properties captured the imaginations of scientists and the public alike. Einstein's theory also provided the first hints about the expansion of the universe. His equations initially described a static universe, but Belgian physicist Georges Lemaitre later showed that general relativity naturally allowed for an expanding cosmos. This paved the way for the Big Bang theory, which describes the universe's beginning as a hot, dense state. Section 7. Relativity's reach, GPS, gravitational waves, and the future of technology. While general relativity revolutionized our understanding of the cosmos, its impact extends far beyond the realm of telescopes and observatories. The theory has had a profound influence on technology, shaping the world we live in today in surprising ways. One of the most widely used applications of general relativity is the Global Positioning System, or GPS. GPS satellites rely on incredibly precise timekeeping to determine your location on Earth. However, time moves slightly slower in stronger gravitational fields, as predicted by general relativity. To ensure accuracy, GPS satellites must take these relativistic effects into account. General relativity also predicted the existence of gravitational waves, ripples in space-time caused by the acceleration of massive objects. These waves were directly detected for the first time in 2015, a century after Einstein's prediction, opening a new window into the universe and ushering in the era of gravitational wave astronomy. Section 8. The Quantum Challenge Unifying Relativity and the Subatomic World. Despite its successes, general relativity is not the final word on gravity. The theory, which works beautifully on large scales, breaks down when applied to the microscopic world of atoms and subatomic particles. This is where quantum mechanics, the strange and counterintuitive theory governing the behavior of matter at the smallest scales, comes into play. Quantum mechanics and general relativity are fundamentally different theories. Quantum mechanics describes the universe in terms of probabilities and uncertainties, while general relativity relies on a smooth, continuous space-time. Reconciling these two pillars of modern physics remains one of the greatest challenges in theoretical physics today. Physicists have been searching for a theory of quantum gravity, a framework that can unify these two seemingly incompatible worlds. Such a theory would be a major step towards a complete and consistent description of the universe, from the smallest particles to the largest cosmic structures. Section 9. The fabric of reality. What is space-time and where does it come from? Einstein's general relativity forever changed our understanding of gravity, replacing the Newtonian concept of a force with the curvature of space-time. But this begs a profound question: what exactly is space-time? Is space-time a fundamental entity, a canvas upon which the universe plays out its drama, or is it an emergent property arising from some deeper, more fundamental structure? These questions lie at the forefront of modern physics. Perhaps space-time, like the atoms and molecules that make up our world, is not as continuous and immutable as it appears. Could it be that at the Planck scale, the smallest possible unit of space and time, the fabric of reality itself becomes granular and fuzzy, governed by the laws of quantum mechanics? The answers to these questions remain elusive, but the quest to understand the true nature of space-time continues to drive our exploration of the universe and our place within it.